Spanish on you? Haha! Yeah, I just want to make sure that Mike picks that up because I expect a lot of applause today. All right, filing. Okay. The agenda for today is I'm going to draw my board. The agenda for today is we are going to briefly review the quiz a little bit. I don't have the whole quiz, but we'll just talk about this one problem with drawing the temperature and heat rate and heat flux distributions. We are then going to do some review of control volume and control surfaces, applying conservation of energy, and then working from there. And then we're going to derive internal heat generation with a little bit more formality, because I think you might have a little bit of trouble getting it out of intuition. But basically the processes that we did last week, that step-by-step thing that we did for the slab and the cylinder without internal heat generation, it's exactly the same loss. Any requests? Pretend this is like a karaoke night. Does anybody have like a specific topic? Maybe like Van Morrison or. Okay. So just before some of you came in, we were talking a little bit about problem was from 3 on the quiz yesterday. 4, I think. From 4 on the quiz, drawing the distribution of Q. So heat rate, heat flux, and temperature in the cylinder. So the critical thing is if this is our cross-section of the cylinder, we're interested in going from the origin out to R equals R naught, your outer radius. So starting with heat rate, as you move further out, you're capturing more and more volume of the cylinder. And your Q gen, or I guess your Q at any point, actually we'll just start with an arbitrary. So you take an arbitrary slice, right? An arbitrary cylindrical control surface. So it looks just like the cylinder, centered at the origin, but somewhere between the origin and the outside of the cylinder. Your total heat rate through this cylinder has to be exactly equal to QR has to be exactly equal to all of the energy that is generated inside that control surface. So, or you could say in the control volume bounded by that control surface, because there's no extra heat coming in, right? So there's no original heat flux or heat rate. So basically, in this steady state condition, if you've got heat passing through a control surface, it has to be generated within that volume. That is just kind of an application of first law that should be hopefully somewhat intuitive. So Q at R is exactly equal to Q big dot. I think that's what we're using for Q gen, which is in watts per meters cubed, times cylindrical control volume. So what is that? Q dot times, what's the volume of an arbitrary cylinder?
Pi r squared L.
Pi r squared L, that's our number there. So basically, as R increases, your volume increases not linearly, but quadratically. And if your volume increases quadratically, and your Q gen is a constant watts per meters cubed, then your Q, your heat flux through that control surface should also increase quadratically. So that gives the first one. Any questions so far? Okay. Challenge question. So heat flux. Heat flux is exactly equal to your heat rate, Q, over your area. Now, as your radius goes out, your volume increases, but so does your area. However, they don't increase in the same way. So your volume of that control volume, pi r squared out. Your area of your control surface, right, which is the thing that's bounding the control volume, increases as 2 pi r out. So everybody remembers that? Okay. So if we're interested in heat flux, Q over A, that's Q dot times V over A, and you can expand out those terms and then cancel. And what you end up with is Q dot times R over 2. So basically your heat flux increases linearly with R. This gives you your second curve. Temperature distribution. I have to think a minute about temperature distribution. Your temperature distribution is going to be highest in the middle. Can we agree on that? Thank you for joining us. Okay, let's think about this. Your temperature distribution is going to be highest in the middle. Do we agree on that? Right? Because you're basically, I mean, imagine you don't deal with a lot of like hot things that are continuously generating heat. But if you're holding what? Sun. If you're holding the sun, which most people don't deal with in the daily life. But you know, if you're holding like you guys know this like electric heating pads. So if you wound one up, if you rolled it, you can imagine it would be hottest in the middle, and then it would come down to some non-zero, certainly non-zero temperature at the outside surface. Now, what that temperature ultimately is a function of stuff that's going on outside of the cylinder. So depending on what your ambient temperature is, what your heat transfer coefficient on the outside is, but it's going to come down to some non-zero temperature. And then the question is just how it comes down. So if we know Q, no heat rate. I just have to think about this one for a minute. I mean, my best guess is like this. What did you guys draw?
I drew that and the atom was fixed at the outside, so it went down to the.
Yeah. Hello. Hello. So intuitively, I want to say it goes like this. I mean, the other option would be it goes like this. I'm trying to think how we could do that formally.
Because heat flux is increasing as you increase your R, so you have a greater temperature distribution. So it's like you, it's steeper right hand side.
Say that again?
So because your heat flux increases as your R increases, you have a greater slope of your temperature on the right hand side.
That makes a lot of sense. So yeah, so without going into the big formality of doing like a Fourier's law derivation, where you have to do all the substitution, you say, if you've got more Q, then the temperature and the material doesn't change, and we know that it's a very good answer. Is this still okay? So if we know that, okay, let's use Q heat flux is negative K dt dr. So we won't include area. We've already gotten heat flux, so we know it's linear, which is frankly easier to do with a quadratic. So if this is big and K is the same, and is the same, then dt dr has to be big, right? So this is T versus R, so the slope, negative, positive, whatever, it's got to be steeper. So it would make sense then that on the outside where you've got a higher heat rate, you've got a steeper temperature curve. I think that's the answer. That's all you really need. You didn't need to do some crazy derivation there. Just that kind of, we have an idea of, just kind of inspection of the governing equation. So I think that's that problem. I hope it is. I'll check with Professor Burke, but I think that's basically everything you would have needed to do for problem 4. And that's the critical thing, is you didn't need to do some like energy balance nutty thing. You just kind of, you know what's happening with V, you know what's happening with A, you know what's happening with Fourier's law, and you just kind of sketch it out. And then there's a little bit of intuition too, right? So, we know it's not going to go to zero temperature on the outside of something that you probably won't be able to that, unless you labeled it as zero. If you're like absolute zero on the surface of the cylinder, then you might. Okay, so that's the first problem. Any questions on that from people who were here? Yes.
So if we use this instead of like actually solving like the fourth order, fifth order equation, like how do we know when to actually derive the formula and like estimate using like rules like this?
So far we've only seen fourth order equations for radiation.
Oh, but if you were to like actually solve the heat transfer equation for this cylinder with the generated, I think it's like a fourth order, x1 to the fourth or to the fifth. The heat diffusion equation? Yeah, the heat diffusion equation.
I don't think it will be. Well, actually, why don't we, on the itinerary for today as we solve this more formally, why don't we roll right into that now? Okay.
Can your shapes look different if you have the opposite sign?
If you had like an internal, if you had negative energy generation, which
I think for me, like I did it out with like the ODEs and
With what?
like the differential equations, and I ended up having a lot of constants, but I didn't know the sign of.
yeah, I mean certain constants always have the same, like, so thermal conductivity is positive, right? And the reason that there's a negative term in Fourier's law is because by convention thermal conductivity is positive. If thermal conductivity were negative, what would that mean? That would mean that heat would spontaneously flow up thermal gradients from cold places to hot places, right? Now that doesn't actually break the first law, right? Because you can still have conservation of energy if heat's flowing in the wrong direction. It breaks the second law, right? You'd have things, entropy spontaneously decreasing, which wouldn't be good for the universe. I think the critical thing, the point of these exercises is we don't want you to have to go into the backbreaking exercise of doing really formal derivation. If you can do this this less formal way, where you just kind of pick out the terms and intuit what you need, then once you've built that intuition, it's very helpful when you're doing the more formal stuff because you're more grounded in kind of a general understanding of what the shapes of these things should be. So you should be able to look at an internal heat generation problem that's kind of arbitrary and have some feel for what your max and min temperatures are going to be, or like where at least you would find a max and min temperature. So kind of by intuition, it should make sense to us that if you've got internal heat generation in a cylinder or in a sphere, it's going to be hottest at its core, right? Even though the heat flux is the smallest there. Yes.
In the negative R direction for Q, is it like?
Can you speak up a little bit?
For the negative R direction in Q, does the parabola decrease like concave down or concave? Is it?
Oh, when you go.
Yeah.
It should just. It's a little because there's no negative R, right? If you think about cylindrical coordinates.
Okay.
Yeah. So if we think about cylindrical coordinates, I know this is the Cartesian axis, but so R is always positive, right? You've got R, you've got Z, and then you've got theta. So if you want to define any space, you might say R is 1, theta is 45 degrees, and Z is 2. And that puts us 1 out, 45 in, and then 2 up, and that's your point. So there's really no negative R. What there is, if you want to get at the opposite point in the cylinder, it's theta plus or minus 180.
And it would have the same distribution for
Yeah.
the corresponding
That's
positive.
the thing that we're dealing with linear. This is one-dimensional. It's kind of funny. I think we talked about this a little bit last time. I know that cylindrical and spherical coordinates might feel a little bit unfriendly, but it is amazing how much we're able to do with what is fundamentally a pretty complicated problem. because you've got heat transfer at 360 degrees around. And by exploiting cylindrical coordinates, we're able to model it as something that's only a little bit more complicated than a slab, which we should be happy about that. Did that answer your question? Okay. But yeah, basically this applies no matter which way you point theta. It's with the steady state assumption, with this kind of one-dimensional assumption, it's independent of theta and z. Yeah, it applies anywhere you rotate your perspective. Okay, everyone feeling good so far? Okay, I'm going to erase the board, and then somebody who was here last week, we're going to write out my like 7 steps, plus there were some intermediate steps. I think Nevada was in there. We're going to update it to South Carolina for this week. And then we're going to do the cylindrical internal heat generation problem. I kind of want to start with internal heat generation in the slab. We're going to start with internal heat generation in the slab. We're going to do a formal derivation of that. So this kind of connects what you were doing on your quiz and what other students might have been doing. And then if we feel good about that, we can try to do cylindrical too. What? Actually, control volume, I think, was first.
Yeah.
Control volume. 2.
Energy balance.
Energy balance. This is Noah's 7-step program. 3. Analysis trip. 4.
4 years long.
4 years long.
Fourier's law. Was 4.5? What was it?
That's was sometimes there.
What was 4.5? Assumptions.
Can't we just make that like 5?
Which includes.
Nah, we did it last week. We got a assumptions basically is we've applied Fourier's law, and more often than not, we're going to be taking some terms out of Fourier's law to make the math tangible.
Boundary conditions.
5 is boundary conditions.
No, 5 is all ODE.
What? Oh, 5 is ODE. Nadia, you're just trying to do this from memory.
No.
ODE.
And then BCs.
Oh,
6 boundary conditions. 7, was there 7?
Solve for resistance. And then,
Wait, what was it?
or solve for the resistance.
Oh, 7 was optional resistance. And then where was Nevada?
It's 4.5. Yeah.
Nevada. So we're going to update this to South Carolina.
What do you do next week?
Well, Super Tuesday is coming up, so that's going to be. That'll be my review session. I'll just go through everything. Okay. Great. Control volume. Let's start with a slab. Okay, so the problem we're solving is a slab with internal heat generation. There's a lot of things that you can model as a slab with internal heat generation. If it's thick enough, so actually heated floors are a real thing in buildings. You guys ever use a heated blanket? Have you guys read that little thing on the heated blanket that says like, don't cover it with other blankets because it's a fire hazard? Have you guys seen that? So a problem that I'd like to solve with you guys, probably not today, but how many blankets do you actually have to stack on top of the heated blanket such that the core temperature will rise to 451 or whatever the spark point is? We'll deal with that later.
Clothes for that?
No, we don't. This is kind of on theme with the New Hampshire recitation, since it's cold weather stuff. But maybe one like Wisconsin or Milwaukee, or Michigan's voting, we can go and do that problem. Okay. Okay, so we're gonna start with. So you've got a slab. It's got volumetric internal heat generation. Volumetric, so it's Q dot, and that's going to be in watts per meters cubed. And later we're gonna need to assume it's constant. Right now we haven't really assumed that yet. I don't think we have to. You've got internal heat generation. We've got K, thermal conductivity of the slab. We're gonna make that constant. We're gonna have a surface temperature that's gonna be the same on both sides. I think this is really just a more formal version of the problem that at some point you guys had on homework. Now, per what we just learned with a cylinder, what do you just expect very roughly the temperature distribution to be inside the slab? It's going to be hotter in the middle, colder in the middle, hotter. Yeah. So right in the middle, we expect, and this is not an assumption, we're just kind of inspecting the problem, which is a really good thing to do before you start the 7 steps. Maybe that's the 0th step. Just look at it. Just commune with the problem, like you're among the trees. We're communing with the problem. Okay, you've got thermal conductivity, you've got temperature distribution, or you've got surface temperatures. You expect it to be a little hotter in the middle. Is it gonna just angle up and then just like meet in the middle, just like 2 lines? No. It's gonna curve. It's gonna be a nice, peaceful curve. Does anybody have a non-intuitive reason? Well, it's not unintuitive. Intuitively, it just kind of looks nice, right? It just kind of peacefully meets in the middle. Does anybody have a slightly more formal reason, without going through the whole derivation, a slightly more formal reason why it would be shaped like this?
Is it because the internal heat generation is probably like centered in the body, so that it won't have that big of an effect on the surface's temperature? So the rise would be like higher because of it.
Not quite. The internal heat generation is perfectly uniform. So every tiny little cube you could draw in this body has the same, no matter what the orientation or angle is, it's going to have the same internal heat generation in any little element. So it's not centered, it's completely uniformly dispersed. Any other reasons why that curve might be, the temperature distribution might be shaped like that?
Does it have to do with continuity? Like,
A little
like
bit.
if it's like that, then that, I don't know, there would have to be something weird happening in the middle.
Yeah, more or less. It's basically it's a symmetrical condition. I mean, you should be picking up by now that this problem is completely symmetric, right? Everything, if you drew a line in the middle, everything's happening on the left is happening the opposite direction on the right. At the middle, is heat flowing to the left? Is it flowing to the right? No, there's no heat flux at the middle, right? There's no reason for heat to want to flow from the left side to the right side or the right side or left side because it's perfectly symmetric. So if there's no heat flux at the middle, what does Fourier's law tell us the shape of the temperature distribution is going to be? Yeah, so Q double dash Q flux negative K dt dx, right? So if Q is 0 and K is not 0, then it's dt dx that has to be 0. So it's going to be flat. Okay. I would say we have sufficiently communed with the problem. Oh, so now there's a little simplification. This is all still prologue. This is before we get to control line. Because it's symmetric, we can do something else to simplify the problem. It's going to help us a lot in step 6. We get the boundary conditions. So right now the boundary conditions are constant surface temperature at both. We're going to make a simplification now that's going to help us later. We're going to have an insulated boundary condition. And you're going to say, Noah, how can we have an insulated boundary condition if we know that there is positive heat flux coming out both sides of the wall, right? This is not insulated, right? Right? Okay, how can we do it anyway? It's not, yeah.
Cut it in half.
Cut it in half, exactly. Because there's no heat flux, we know that there's not going to be any heat flux right in the middle. We can essentially just erase half this problem. And we know that from the middle, it's the equivalent of having an insulated boundary condition. Because there's not going to be any heat flux past that center point. So if originally this thing was L wide, the thickness of the slab, now we're dealing with half a slab. The length is L prime. or L star, which is L over 2. And instead of having a temperature surface boundary condition and instead of having two constant surface temperature boundary conditions, we're going to have one constant surface temperature boundary condition and one zero heat flux insulated boundary condition. That's what insulated, when we say insulated boundary condition, we just mean no heat flux. When you say insulated tip in the fin problems, it's just no heat flux through the tip. Okay, so I think we're done commuting with the problem. You guys are just going to have to suspend disbelief and kind of follow along with me for a minute that this is all useful. Okay, feeling so far so good? Okay. You guys, I can tell you guys are a little more tired than you were at the beginning of the semester. Okay, so that was all step 0. Let me actually write commune. Commune is spelled the same way as commune, right? But let YouTube know it's not commune, it's commune. Just okay.
Can YouTube see the board?
Sorry?
Can YouTube see the board?
Who watches the YouTube videos?
I
Right here.
tried once in the first lecture.
You can't see it?
Oh, yeah.
Well,
Definitely gonna love.
all the more reason to come. Recitation.
Yeah.
You know what? Hold on. I can probably help with it. So control volume is just an arbitrary slice somewhere between, we'll say this is x equals, so this is x between 0 and L star. We're going to take a little differentially thick slice. So this slice, it goes from x to x plus dx. And it just has to be somewhere in this domain, right? Between 0 and L, we're taking a little slice that goes from x to x plus dx. Okay, so that's our slice. Now we're going to do the control volume analysis. What do we know about that control volume? I'm going to redraw it, just at kind of a better angle, just a little squatter, so we can play with it. So imagine this is the whole slab, but just drawn a different perspective. Okay, this is our CV. Okay, what's going on with the CV? How do we do our step 2, our energy?
There's internal generation.
There's internal heat generation, so there's going to be a QD term, right? What else?
There's heat coming
Out.
both ways, sideways.
It's actually only flowing in and out. That's the nice thing about the insulated boundary condition on any given side. I mean, we knew that from the temperature distribution, right? We know that if the temperature distribution sloped down like this, heat's only going to be flowing this way. In the other direction, the side that we're not looking at right now, it's only flowing in the other direction. But basically, you've got heat coming in, you've got some heat being generated, and then you've got heat coming out. So our energy balance is Q in plus Q gen equals Q out. And all of this, you just think about this as in units of watts, okay? Even Q gen, right? Even though we're doing this over a differential element, think about it in units of watts. And we're gonna kind of work through the calculus and make that make sense. Over a differentially small element, Q gen is gonna be infinitesimally small, right? But again, calculus tricks. Okay, so the other way to write this is Q in is your heat flux Q evaluated, and Q, the convention is this is just one dimensional across the x-axis going to the right. Q evaluated at x plus Q gen. And Q gen is, since we're assuming uniform volumetric heat generation, it's Q dot times the volume of this control volume. So we've got a control surface here, right? A control volume here, and there's another control surface at x plus dx.
Wait, so you're saying that the volume is the volume of the control volume?
Yes, the volume is for now, for this control volume analysis, we're just dealing with that little volume. Yeah. So, I'll write that V sub CV, volume of your control volume, which is this differentially thick, but full area. It's the full area of the slab, but it's just a tiny thin slice of it. Gotta save time for the onion. Okay, what's our next step?
The analysis trick.
Analysis trick. What's the analysis trick going to do for this problem? Actually, there's one more thing I want to expand on before we get that. I apologize. VCV. What is VCV? I just said it actually. Was it?
Volume of the control volume.
Volume of the control volume. Yes. So we can replace that. We can rewrite it as QX plus Q dot times the volume of the control volume is A, the area of the slab, times dx, right? Because that's the distance between our x and our x plus dx surfaces, right? They're just dx apart. X plus dx. Okay, now the analysis trick. We're going to bring qx over to here, over to the right side. So on the left side, it's QA dx equals Q x plus dx minus QX. Technically, this is, or not quite the analysis trick. I think we have an algebra step in there somewhere, but it's all. So what is the analysis trick? What do we do?
Take them with you.
Nah, not yet.
Oh, divide by.
Divide both sides by dx. And in the past, when we divided by both sides by dx, it was kind of lame because there was no dx to divide by. We were just making up a dx and then saying, well, the left side's 0 or the right side's 0. 0 over dx is still 0. Now we actually have a dx to move, so it makes a little more sense. We're going to divide both sides by dx. Cancel out the left side. And now we've got something that looks an awful lot like the definition of a derivative, right? So I have forgotten my math education. There's some formal stuff I'm supposed to do where these are like, I don't know if these are deltas, and I take it delta x goes to 0, or they're d's and then goes dx goes to 0. But we all know that this is what the derivative looks like. So whatever the limit, proper way of writing the limit is, we're just going to replace this with dq dx. That's our analysis trick. This thing is the very definition of derivative, so it just becomes dq dx. And now it's the left side, q dot a. So watts per meters cubed times an area, which is meters squared. So you've got something in terms, essentially watts per meter over here on the left side. And then this is watts, but it's derived, differentiated with respect to x. So this is also essentially just watts per meter. Feel good so far? Okay. What's our next trick? Our next step? Fourier's law. So Fourier's law, we're going to apply to Q, and we're going to expand out that term, Q term, d dx. I'll replace Q with negative k a dt dx. Okay. I'm going to rewrite this just down here to make it a little cleaner. So I'm going to just swap the left and right hand side. d dx minus k a dt dx equals q dot. So in the past, your right hand side was always 0. So basically, when we took stuff out of this derivative, took out k and a, we just divided them out of the whole problem, right? You divide both sides. If you take these out of the derivative, divide both sides by ka, it's just 0 on the right-hand side. We can't do that anymore because we've actually got terms on the right-hand side. But the step 4.5, South Carolina, is assumptions. So what assumptions can we make that is going to make this calculus workable?
A is constant, K is constant.
A is constant, K is constant. Constant thermal conductivity, constant surface area. Now, by the way, you don't need to make these assumptions. Like, you can still do these kinds of problems without these assumptions. So if you had thermal conductivity changed over X, and we've seen that a little bit, you can still come up with a closed form solution for most of this stuff. It's really no different than having a cylinder where area changes with R, right? So we basically have the calculus tools to deal with a pretty broad range of kind of weird as long as there's still like continuous differentiable conditions for K and A. But for right now, we're going to assume constant K, constant A, -1, always constant. So we can take all this stuff out, and now it's negative KA, and now it's just ddx of dt dx. We're going to make that, actually we'll just keep it, we'll write it out longways. ddx dt dx. Equals q dot a. Okay, what next?
Cancel the A's.
Cancel the a's. Cancel the 1. Oh, actually, we don't want to cancel 1. Well, we'll bring the negative k over. So now we've got ddx of dt dx is negative q dot over k. Okay. Got a little slightly limited space. I'm gonna just erase this thing, which is fine because we rewrote it. So basically, we're just going from here and here to this is over here and this is over here. Can you see this on the screen? Yeah. Sorry?
If someone watches that, and they're gonna see you go, can you see this?
Yeah, can you? Better be nobody watching. I would be so upset if somebody was watching live at home right now. I had to be here, and you guys didn't. Incidentally, once Corona hits New York, all of this is going to be YouTube. I'm not going to come in the mud. All my TAing is going to be remote. I'm going to be at home. I'm going to be with my cat. It's going to be great. Okay. Oh, so this stuff can cancel. Okay. So we've applied. We're going to stop talking about non-heat transfer. We've applied our assumptions, and now we have an ODE. So what is the solution to this ODE? Basically, negative is always constant. Q dot, we're assuming is constant. K is constant. So basically, this whole thing, you can just call that C1, right? So you've got ddx of dt dx is equal to a constant. Why don't you guys all take a minute to solve that ODE? Because this is the level of ODEs that you should be able to do on them. Okay, how are we feeling? Does anybody want to do it on the board?
No.
Live for the internet?
No.
Do it! Cool. I'll share with you, I'll tag you, you can have some of my followers.
It's okay. Some of my followers.
I think I have 2 followers.
I subscribe.
You subscribe?
Yeah, for
Yeah, Q and K are both constant.
So.
Everybody applause.
So because we have uniform energy generation and conductivity is a constant, when we take ddx of this expression, we know that we have a constant, meaning that when we integrate that, basically, we can add.
Use the board, use the, yeah.
So when we take. Because the other side was a constant, we know it's just a term that gets multiplied by x. And then we add on a constant from the integration because we don't have limits yet. So you can just like, if you were to take the derivative of this again, you can see that it turns into that. And then from there, we have one more antiderivative to take, right? So we do it with respect to x, we have dt.
Looks all right. Like and subscribe. Isn't it hard to write on a chalkboard if you're left-handed?
Yeah,
It's really hard to do it well.
because you're dragging over your word.
Yeah. All right, who else is left-handed? Is it just us? Okay. That is absolutely correct. So I'm gonna erase the original picture. I hope you guys are okay with that. Okay, what's our next step? We've done boundary conditions. Oh, well, we haven't done boundary conditions. Our next step is boundary conditions. Sorry, I ruined the surprise. Okay, what are our boundary conditions? Oh, I just erased the picture, but I changed them. Remember, I changed them at the beginning, and it's going to make it easier, I promise. So what's our first boundary condition? Insulated, yeah. So at our new x equals 0, and basically we're redefining the origin. We're sliding the whole problem over so that the x equals 0 is right at the origin, and then x equals, that the other side is x equals L star, right? Which is really L over 2. And it's a cool thing we can do once you realize that Cartesian coordinates are totally arbitrary and they're just made up by some guy who didn't really do science. You can apply them any way you want. That's the Cartesian way. Okay, so at x equals 0, we've got q equals 0. And at x equals L star, you've got what? T equals TS. It's something. We don't really know what it is. When you start doing, maybe later we'll do some real problems where you've got internal heat generation and other stuff. Those problems are a lot of fun because what you end up doing is, I'll show you after. But it's some constant temperature surface condition. Just accept that for now. Okay. If q equals 0, right, and q is negative k dt dx, and k is constant, then what does that mean also equals 0? dt dx, right? So if q equals 0, that implies dt dx equals 0. That there is q0, there is no slope, there's no temperature gradient at that point, at the origin, which we already discussed at the beginning. That's how we got the shape of that curve. Sound okay? Yeah? We have a question.
I understand it now.
Sorry?
I understand it now.
You understand? Okay, yeah.
Quick more questions.
Yeah. So q, remember, q equals negative ka dt dx. Now, so if that's 0, then k and a are not 0. So basically it means that dt dx has to equal 0. So no slope. So if q is 0, if it's insulated, then dt dx is also equal to 0. Okay, dtx dx is 0. I think that's the easiest one to do first. So this is our final temperature distribution pre-boundary conditions. So what is dt dx of that? What's dt dx of that? It's going to be just negative q, negative qx over k plus c2. Negative q x over k plus c2 equals 0. Now, that's only at x equals 0, right? So let's just replace that x right now with a 0. So if that x is 0, this whole term goes to 0. So now we just know c2 equals 0. Boom! Insulated boundary condition. It's magic. So this whole thing, bam, it's gone. Forget about it. Erase it, cross it out. So now we've just got this quadratic term and a constant. How easy was that? Okay, so now at x equals L star, we've got T equals TS. So T equals TS equals negative Q dot x squared is now L star squared over 2k plus C1. Okay? So, I don't even want to keep that up. So then what's C1? You just move the first term over, you're done. C1 is exactly equal to, because all of these are constants, basically, right? This is all stuff that we know. So C1 is just TS plus Q dot L star squared over 2k. So now we'll write our final temperature distribution is T equals negative Q dot over 2k x squared plus C1 plus TS plus Q dot L star squared over 2k. And we can, I'm gonna erase this part now. And we can just bring these terms together, right? And the way to do that is we basically realize you got Q star over 2k, Q star over 2k. The only difference is L squared and X squared. So we can just write T equals TS plus Q dot over 2k times L star squared minus X squared.
Could we replace L star with L over 2 from the?
Yeah, sure, why not? Let me do it now. L star is just L over 2. I feel pretty good about that. How do you guys feel about that? So let's just do a little bit of inspection. Okay, so at x equals L star, or x equals L over 2, what's the temperature? TS, exactly, right? Because it's L over 2 squared minus L over 2 squared, which is TS. What is the maximum temperature? Where is the maximum temperature? Who is the maximum? No, where is the maximum temperature? The maximum temperature we believe is going to be at the origin. We can prove that with calculus, right? If we just differentiate that and then set it equal to 0, we're going to find that 0 slope place, and that gives us at least a local extremum. But let's just say that we all get the problem well enough to know that it's going to be at the center. We're not going to prove that right now. What is it though? We plug in x squared equals 0, and you get T max, which is just equal to T at x equals 0. We know how to prove that that's where it is. Equals TS plus Q star over 2k times L over 2 squared. Now the funny thing is, this is actually in terms of what's the units of this whole term? Kelvin, or Fahrenheit, or Rankine, or whatever. Inverse Clow times, I don't know, but it's in units of temperature. So this is the temperature, right? And what drives this temperature? So if you want a hotter temperature at the core, what do you do to the size of the slab? Make it bigger, smaller? Holding everything else equal. Bigger, yeah. So as you increase the thickness of the slab, L, the temperature at the core increases quadratically. So that is your kind of your strongest signal that this slab is essentially self-insulating, right? So if you want it to be really, really hot in the middle, you make it bigger, and as you make it, if you double its size, you're going to quadruple the temperature, or at least the added temperature, the extra temperature over the surface temperature at the core. The interesting thing though is the world, length scales in the world, you can double something, you can triple something, it's hard to make it 100 times bigger. You can make something 100 times worse a conductor. So if you want a really hot temperature at the core, and you say that this internal heat generation is like wires inside of a material, if you bring the conductivity of that material down and you make a really insulating material, then if something's 100 times worse of a conductor, it's going to be 100 times hotter, or at least that temperature difference, the delta T between the surface and the center, is going to be 100 times hotter. Is that true, right? K is on the bottom, right? So you decrease K, you increase your temperature. Certainly you could increase your Qgen, right? So you just put more watts into it. If you have an electric blanket at 110, plug it into a 220 outlet, see how it goes. Yeah, those are pretty much your mechanisms. Or you can just increase the surface temperature, right? The whole room, if it's in a hotter room, it's going to be hotter. Yeah, so that's your temperature, your maximum temperature at the core. I hope that kind of proves out some of the stuff that we've been doing more conversationally with internal heat generation, and this gives a little more formality. But the nice thing is, at least this approach, which is the one that I favor, I think your book has both. There's like a classical and the alternative in income prayer. This is pretty close to, I think, what they call the alternative one. Makes a lot of sense to me, because you don't even need the diffusion equation at any point. You're just kind of starting with first law, one-dimensional assumptions, and then plugging in Fourier's law. And you don't need to have a whole big complicated diffusion equation. But you should be familiar with both. I think Professor Burke favors starting with the diffusion equation and working from there. Okay.
Yeah. Is it actually a wall?
I think it's a Spanish onion.
Yeah, it's not a wall.
69 cents a pound. Okay, so I suggested I might do this last week. Okay, actually the first thing is I'm not planning on doing a full derivation of internal heat generation in a cylinder. What I would tell you is the process is exactly the same as what we did. The only difference is you've got non-constant area. But if you guys follow the ODE through, you basically are replacing A, which was constant and canceled out, with 2 pi RL, and then you move it over, and the ODE comes out a little bit differently. I don't want to take the time to go through the whole thing. I think it's in the book. It was not in that book, and I'm sure it's in a different book, and I can find the derivation for you guys. I don't want to spend another half hour doing that right now. But same process. Those 7.5 steps, 8.5 steps, all apply in the same way. The communing part is basically the same. You should basically have the same intuition with a cylinder with internal heat generation as you do with an insulated slab. Okay, so we're going to leave that there. The point of the onion example is just to really pin down what's going on with Q and Q double dash. And while we're at it, control surfaces and control volumes, which we haven't really been speaking about formally. I think the problem is we've had this kind of colloquial language of like, what is Q at R? And we haven't really defined Q well enough. What we mean when we say Q. And I think part of the reason for that is we've got these one-dimensional steady state assumptions, and most of the class is based on that. And those assumptions make it easy to avoid getting into a lot of like really hardcore detail, but sometimes that detail having formality helps. Okay, so in the interest of formality, I'm going to start cutting an onion in front of you guys. Can anybody tell me why I brought in an onion? Oh no, this onion.
Ogres have layers.
This onion, because onions have layers like ogres. Oh, that's why the guy was, yeah. Okay, this onion, unfortunately a lot of onions are not perfectly concentric in the middle. That doesn't quite work. So there's some extra stuff, but we're going to just try that out. This is not the right
Can I
name for
just
this.
make a comment about Corona beer while you're cutting the onion?
Sure.
Corona beer does not cause coronavirus, but a survey shows that U.S. purchase intent is down.
Yeah, one of my friends said that he's gonna buy some, like, stocks in Corona in like a couple of months because he thinks it's gonna be super cheap. Let alone not. So if anybody wants to invest.
Can we short Corona stock?
I think it's too late for that.
No,
I
it
think-
keeps going down, short it now, because that's the betting, it's still going down.
I mean, yeah, but like you're
It's
gonna,
when you
Buy
get
it.
it.
Jonah, your pasta stash is gonna be so good when the apocalypse comes.
Oh, really?
Best friends.
Best friends on Snapchat. Mitch and I.
Aww.
Sorry, I thought this would go easier.
I said like 2 times though.
There we go.
Finally came through.
Listen, yeah, I think I have that.
Okay. Yeah. Okay.
Yeah.
Okay. Anybody like that? Okay. This is all I wanted.
I'll take them.
Okay, so the point of the onion is this is our spherical shell. Instantly, have you noticed when we were doing the slab, kind of the cylinder and it was always a cylindrical shell, it was always a spherical shell, right? It was never a solid sphere, it was never a solid cylinder. Anybody tell me why that is?
Why it's not a solid sphere?
Why we never did the math or tried to do the math with a solid sphere?
Like what heat transfer application.
Cause 1/r.
Because there was a 1/r and a ln r term, right? And with both 1/r and ln r, you get non-real or like non-finite. So do you guys remember what 1/r is shaped like? I guess I can still touch the chalk with onion. So 1/r looks like this, so it's not defined at 0. And ln r looks like this, so it's also not defined at 0. Okay. So that's why we were working with the shell. So this is our shell. So I just want to clarify. So when you kind of the shell problem, you're assuming that there is some sort of generation in here, and it's a constant heat rate. So imagine there's a resistor inside this onion. Why not? And it's always generating, really transferring from electricity to heat 20 watts, right? You got a high power phone charger inside this piece of an onion. Through each layer of this onion, what is your Q? What's your heat rate? Yeah, it's always the same. That's the critical thing, is your Q, assuming not internal heat generation, we're stepping away from internal heat generation. When you've just got that, shell resistor type of problem, Q is always gonna be the same. But then what happens to Q double dash, your heat flux?
That changes changes.
Yeah, it changes, areas changes. And how does the area change? So if I start, I want to show you. So if I start from the small radius, so this is the area, very small radius. And then as the radius increases, how does the area change? Sorry, just for YouTube. As the area increases, or as the radius increases, do I end up with bigger area? What happens? As the radius increases, I get bigger area. Okay, that was the whole point of this. Weeks in the making. And we handed out half an onion. Does anyone have a water bottle?
I feel so attacked.
Attacked?
By the onion smell.
Yeah.
Oh, I'm sorry. Who complained about the marker smell yesterday?
That was me.
Like everybody in the front row was just dying to say it, but Adela was the only one who had the courage to do it.
You gotta clean out your lid of this.
Yeah, I tried. Wow.
Thank you, though.
You're welcome.
I don't want to see the picture. All right. Okay. That was the whole point of this onion exercise. Okay, yeah. So basically, Q is constant, but Q double dash, which equals Q over A, which for the sphere is Q over 4 pi r squared, right? That's the surface area of the sphere, is going to decrease quadratically, or decrease with 1 over r squared, which looks like this, I think, right? And as you go all the way to the center, your area goes to 0. Well, actually, I guess you never get all the way to the center, because the thing's only defined between R inner and R outer.
So is that the same as saying, like, for example, if our inner and our outer have a small difference, then our area is larger?
If R inner and R outer. Okay, so I think I know what you're getting at. So the point is, did you ever hear the question? Can you repeat the question?
So, okay, what we're saying in terms of like moving away from the center, does that mean that if your R, let's say you have an onion,
Okay.
that the radius is like 4, like our outer is 4 and our inner is 2. If your inner was 1, then you'd have a larger area than if you had your inner at 2.
Inner was 1. Well, the area is smaller for smaller radius.
No, what I'm saying is like if the wall that you have between
Yeah.
R1 and R2, so that area is getting smaller.
Yeah, if R1 is big and R2 is not that much bigger, you're gonna have a very thin, it's gonna be a very thin walled onion, right? So if I put the onion back together, guys, we're gonna do this in reverse. No, seriously. So this is an onion with a big R1 and R2 is only a little bigger. If I put the whole onion back together, my R2 would have stayed the same, right? It's still this outside layer, but my R1 will have gone smaller. And one thing that will change is that the spherical description becomes more important at that point. When you're dealing with a really thin walled onion like this, it is not that different than just it would be very, very similar quantitatively. When you've got very different R1 and R2, and you've got a lot of kind of spherical mass, then it becomes a different problem, and doing this kind of full-blooded spherical description matters more. I think we did a little example of this with a little numerical example in office hours on Friday or on Monday. Is anybody here for that? A few of you were. So basically what we did was we took an example. We'll do it again now. We did it with a cylinder. This time we'll do it with a sphere. So if we took a really, really big onion, what's the biggest onion you've ever seen?
30 feet.
I believe you. Okay, so take Mitchell's 30 feet. We're gonna make that just 10 meters. Okay. So R naught, you brought it up, and that it helps me numerically. So the R naught is 10 meters, and that's RI, and R outer is just going to be 10.1 meters. Actually, let's make it 10.01 meters. Okay, so it's only we're just going to take the outermost shell of Mitchell's giant onion, and it's just 1 centimeter thick, which is actually very thick for just one onion layer, right? It's a whole centimeter thick. So there's a lot of layers in this onion. So I'm just going to kind of laze over now. Thickness. Stop.
This is the world's largest onion. It's 18 pounds.
Well, this one's big. This one's theoretical, but it's bigger. So
Mitchell's giant onion.
okay. 10 meters, 10.01 meters. Okay, so what is the thermal resistance
Of the onion?
of just the outermost shell of the onion? Can you look up the thermal conductivity of an onion?
Yes, absolutely.
Okay, but everybody else, only Declan's. Do you guys remember, does anybody have the formula written down for the thermal resistance of a spherical shell?
Do we want to fresh and dry white onions?
Declan, hold on to that for a minute.
It's,
Do you have?
is it just like the one that we draw in class?
Yeah, our shell, yeah.
1 over Ri minus 1 over R naught, and I think that is like over 4 pi k.
Over 2 pi k?
4 pi k.
Okay, so this is R.
And then not R, the word should be k.
Okay. Okay. So I want half the room to derive the thermal resistance of just the outer shell of that onion using this. That's everybody with Francesca and Mitchell on this side. And then the other 4 of you, we're going to just do our classic, what is it, L over Ka, K over Li? What's it? L over Ka. Yeah. We're just going to pretend it's a slab. Now you got to compute your area, which is going to be 4 pi r squared. We're going to pretend it's a slab. And here L is really just T, right? Your thickness of that shit. Very, very thin layer of onion. Oh, and then sorry, what's K, Declan?
Okay.
He's reading a research
Let's,
paper.
yeah, I'm skimming a research paper.
Just give me a value.
Let's go with 0.5 watts.
0.5. 0.5. Have I omitted any data you need? Everything's geometric plus thermal conductivity. Yeah. Okay. I'm actually tearing up now, but I've got a lot more on you close to me than you guys do.
They're all gone.
You know, there are these baby toys that you can get that stack cups inside one another that are sphere shaped. Highly recommend for next time you see it.
I can borrow, I mean, Mike's got Professor Burke has 2 young kids, so that would have been a good thing to ask him. But kids are always sick. I'm not gonna get sick from that.
I think college students are actually worse than children.
Yeah, well, you guys have better immune systems.
You know?
Actually, yeah, not with your habits. I went to Mel's when I was a youngin'. I know what you guys do on the weekends. Mel's still exists, right?
Yeah.
Does it?
Also, Havana Central used to be a thing. That was years ago.
Wow, no.
No.
Jack Kerouac used to hang out there, and I hung out with him. That's how old I am.
Would our L value?
That's how young you are.
Would our L value just be the difference?
Yeah. Actually, just gonna flip this. Well, actually, this part of the onion.
If we're pretending it's a slab.
You guys kind of get the motivation behind this. We want to know how necessary the full spherical model is, and to what extent it just makes just treating the thing, just computing the thermal resistance as if it were just this time. Okay, I should have some answers by now. What's the our sphere? 0.0000159. And L over Ka?
What is A in this case?
4 pi r squared.
4 pi r squared.
So how,
And take either one. Won't make a difference.
but how does that act as if it's a slab?
It's the same.
Is it just like we're taking like this?
No, the idea is you're saying you've got, basically the idea is like, if we flatten this, it's the same area, right? And now we've got the slab and it's the same area. And you were trying to put the same Q through it. What would be its thermal resistance?
0.000159.
Okay, so the same. 0.00015. Exactly the same. So when you have this kind of condition where you've got something really big and a very thin wall, it's functionally very, very similar as if you just treat it as a slab. Why does that make sense? It makes sense because this isn't all that spherical, right? If you're looking at it very, very closely, you might not even really tell that it's a sphere. It doesn't have that kind of thickness. Whereas, if we had reassembled the onion, can you guys quickly reassemble this onion for me? How quickly can we put the onion back together?
Not quick enough.
Okay.
Yeah, this is social, guys.
No, mine's.
Sally's.
Most of you guys don't want to touch the onion. Okay.
Guys,
Mine is the last one.
You fit over this
This is fun.
one. Daddy's like, no.
It's really hard to get like the small.
Yeah, this one.
And
I don't
it's
really-
really
Okay, I'll take that.
This is someone else's problem.
Next time, just do orange peel.
No, we need the layers.
Yeah, orange.
Okay, so we've reassembled our onion.
Listen, let me know,
Leeks.
please.
Smart.
Yeah.
Can one of you bring in a leek?
I can't do that.
When we reassemble it, we realize, okay, well, approximating this as a slab, it really starts to look less like a slab, because when you enter here, the area is very different than when you exit. So there's a real significant change in the area as you move throughout your R direction. When you've got just a very thin outer wall, and then you don't. So that's, I think, kind of the takeaway I want you guys to have, isn't that you should just be willy-nilly using slab approximations when you're doing spherical cylinder problems, but that in an extreme example, similar to the slab. Yes?
So when can we make that judgment call that?
Oh, no.
I can- No, okay.
Yeah, you shouldn't actually, if you're solving a cylinder problem, with, relatively small piece of, thin piece of insulation, you could do a little back of the envelope and say, I just treated this as L over Ka, am I close? And more often than not, it's gonna be pretty close, right? If R0 and R1 aren't super different. So we could take a less extreme example and just say, if it were Ri is 5 centimeters and RO is 10 centimeters, I'm not gonna make you guys do the math right now, but you'll see that it's not gonna be exactly the same. If you did that, say do it with a cylinder, look up a real value for insulation on pipe. It's not gonna be exactly the same as if you just did it with a slab, but it's gonna be a pretty good back check. It's gonna be a decent approximation.
And like they should be used like the middle value of R, so like the average of them for the area, or does it not matter?
Yeah, you get the best estimate if you. It's either the middle or it's gonna be like closer to 2/3, just because that's more representative of the kind of center of mass. That doesn't, I wouldn't get a headache about this. But yeah, you could plug in as the, calculate slab, calculate area, at 7.5. You did it at 10 between those two areas. Should. Okay, I think we should call it. There's no homework yet, but the quiz or last week's homework will be over a bit. Thank you guys for coming. I hope I didn't make you cry too much.
Yeah, fun.
Always a pleasure.
Yeah, next week, leaks. And then we'll make soup the week after.
But yeah, and just to follow up on the homework comment I made, it wasn't to say we don't want homework, we really appreciate the homework and the chance to work. We would definitely.
Thanks, Kate, for that. I've been trying to get going on the solutions and I don't have to make it either, so imagine how I feel. As X increases, K decreases.
Well, I'll first start with that. As X increases, T decreases. Therefore, K and T are
I feel like.
And then you're just really
Not directly. I think they're inversely related. I think K and then, so the way that I would think about it is. Well, negative, by the way, Q double dash is negative K GX. So I'm gonna stop the YouTube video.
But in a small way.
Yeah.
And then you're like, I'm not eating.
Seems to have ended. Okay. So we'll just look, the premise of this problem is thermal conductivity increases with T. Oh, that's what you're saying. So,
Thermal conductivity K decreases with T.
yeah, so at the center, we're saying T is high.
Yes.
out here, T is left.
I can't rub the snow off me.
So it's just a matter of how many connections. So Q is gonna be
Every layer.
constant, right?
Every page.
So on the left side, K is high, right?
K would be,
Yes. So if K is big and Q is constant, what happens to dTdx? It'd be small, yeah, so the slope is small here. And here, K is small. What happens to the slope? Is that what I drew? Yes. I apologize if I didn't give enough detail on the solutions.
All right, no, I understand about that.
Yeah, this room's horrifically broken that way. Can you guys prop a door, sure, and the door will be Yeah, exactly. See you guys.
no, look what we made.
Are you sure you want to end your stream? And